Welcome to this deep dive explainer. I am absolutely thrilled to have you here today. We're literally pulling back the curtain to look under the hood of the AI systems running our reality. We hear the term artificial intelligence everywhere, but today, we aren't just skimming the surface. We're going to decode the structural logic, the math, and the architectures that actually power the real world.
Okay, let's dive right into this. Think about your everyday actions. Unlocking your phone with Face ID, asking Siri for the weather, navigating through crazy traffic using Google Maps, or, bouncing ideas off ChatGPT. We're firing through these cinematic, real-world applications every single day. And honestly, it proves that AI isn't some mythical, futuristic magic. It's a highly structural system we already interact with constantly. It is realistic technology deeply integrated into the very fabric of our lives.
So think of our agenda today as a system blueprint. We'll start with AI in our real world, explain machine learning systems and their types, then zoom down into neural networks, CNNs, and transformers before pulling all the way back out to the generative AI era.
All right, kicking things off with Section 1, AI in our real world.
Now, what's absolutely fascinating here is the stark structural difference between traditional programming and machine learning. In traditional computer science, it's pretty straightforward. You give a system the data, the input, and you write the rules, the logic. Then the machine just follows those rules to spit out the output. But machine learning systems, they completely flip this reality on its head. You feed the system the input data along with the final expected outputs, and the machine literally figures out the rules itself. It creates the logic, and that generated logic is exactly what we call the model.
Moving right along to Section 2, Machine Learning Systems Explained.
So the massive explosion of the internet over the last couple of decades, that's what created the massive data sets required to actually fuel these models. But how does the system actually learn from all that data? Well, it happens mechanically in two highly realistic steps. Step 1 is training. Imagine a real-world automated banking system for loan applications. During training, it ingests mountains of historical data, looking at thousands of past applicants, their salaries, their credit scores, to learn the hidden patterns of who pays back a loan and who defaults. Then we hit Step 2, inference. A brand new applicant walks into the bank. The system uses that newly formed logic to make a real-time prediction, instantly deciding whether to approve or reject that loan.
Next up, Section 3, Types of Machine Learning. Let's look at the three primary structures here.
The very first type is supervised learning. This is when models learn from cleanly structured, heavily labeled data. Basically, the inputs and the expected outputs are clearly defined right from the jump. You are essentially handing the machine the answer key to the test, allowing it to mathematically map those predefined inputs straight to the correct outputs.
So, the crucial point is that this supervised mapping actually breaks down into two distinct categories. First up is classification. This is mapping data to rigid, predefined categories, like your Gmail system strictly labeling an incoming message as either spam or not spam. Simple, right? But then we have regression. This predicts a fluid, continuous numerical reality. Like when an app like Zomato gives you an estimated delivery time of 43 minutes, it's not picking from a static list of categories. It's predicting a highly specific numerical value based on real-time distance and traffic data.
But what if you don't actually have cleanly labeled data? Well, that brings us to our other two types. Unsupervised learning finds hidden clusters in raw, completely unlabeled data. Think about grouping millions of daily news articles by hidden themes, or instantly flagging an unusual login as a cybersecurity anomaly. And then there's reinforcement learning. This one is incredibly dynamic. It trains agents via rewards and penalties in a live environment. Think of a self-driving car on a highway. It isn't given the answers up front. Instead, it's constantly chasing positive reward values to stay perfectly centered on the road.
Let's zoom all the way down to the micro level now with Section 4, Inside Neural Network Systems.
Okay, deep learning is loosely inspired by the architecture of the human brain, but make no mistake, it runs entirely on complex math. And this brilliantly illustrates the concept. Imagine a college grading system. If a professor notices everyone is skipping class tests, they might adjust the mathematical weight of that test from 20% to 30% of the final grade just to influence behavior. Well, artificial neural networks do the exact same thing. They assign mathematical weights, biases, and parameters to their inputs. If the network makes a bad prediction, it constantly tweaks those mathematical weights via trial and error to get closer to the absolute truth.
This raw, mechanical reality of training a network basically operates in a continuous two-step loop. Step 1 is forward propagation.
The data moves forward through the network, it computes a weighted sum, passes it through an activation function, and just makes a guess. Then comes step 2, backward propagation. The network evaluates that guess and calculates its exact margin of error, which we call its loss. Then it travels backward through its hidden layers, literally learning from the mistake and mathematically adjusting those weights so the next guess is way more accurate.
But here is where we hit a massive structural wall, 1 million. If you feed a basic black and white image that's just 1,000 by 1,000 pixels into a standard neural network, you instantly create 1 million input points. That means just one single neuron in the hidden layer has to perform 1 million computations. And keep in mind, these networks have millions of neurons. If the image is in full color, multiply that by 3. Suddenly, your computer is literally doing more math for one single cat photo than the entire Apollo 11 moon landing.
So this brings up a massive critical tension. How on earth do we optimize this massive, relentless influx of visual data without completely crashing the system? Because trying to process every single pixel of a high-definition cinematic video, frame by frame, is practically impossible for traditional networks. To solve this, we enter Section 5, Architectures, CNNs, and Transformers.
Let's move to and see how this builds on what we just learned. The sheer scale of real-world data required engineers to build highly specialized architectures, starting with convolutional neural networks, or CNNs. Instead of trying to digest an entire million-pixel image all at once, CNNs use a mathematical kernel to look at optimized, bite-sized patches of an image at a time. They sweep across the visual grid, hunting first for basic edges, then shapes, and finally full objects. This optimization is exactly what allows systems to effectively see, serving as the structural backbone of modern computer vision and self-driving tech.
But wait, what about text and language? Older models, like recurrent neural networks, process sequential data so slowly, just step by step, and they really struggle to remember long-term context. Well, transformers revolutionize the whole shebang. They convert text into tokens and use this incredible attention mechanism to look at the entire context of the data all at once. They compute attention scores to see exactly which words relate to each other in a sentence, no matter how far apart they are. This structural breakthrough is absolutely the foundation for the incredibly powerful text tools we use today.
Which naturally leads us to our final stop, Section 6, the Generative AI era.
All right, we've zoomed all the way back out to the macro level. Generative AI, or Gen AI, is a thrilling subset of deep learning. Up until now, our systems were mostly just classifying existing data, saying this is spam or this is a cat. Gen AI focuses on creating entirely new data from scratch. This is the exact technology powering those mind-blowing cinematic video generation tools like Sora or Midjourney for breathtaking synthetic images.
Now, within this era, we absolutely have to define natural language processing, or NLP. This is the domain where we actually teach machines to understand, interpret, and generate human languages. NLP acts as this crucial bridge. It takes the messy, emotional, complex reality of human communication and translates it into the rigid mathematical structure of machine logic.
And finally, sitting right at the top of the pyramid, we have large language models, or LLMs. These are massive systems trained on a truly staggering amount of internet text. Tools like ChatGPT, Claude, and Gemini, those are LLMs. And here's the thing, they aren't magic. They are exactly what we've explored today, scaled-up neural systems, running heavily optimized transformer architectures, calculating attention scores, and relying on billions of mathematically adjusted weights to generate human-like text.
So we've journeyed from simple traditional programming all the way to sprawling neural networks that literally generate realities on demand. But this leaves us with a pretty provocative final thought. If our real-world systems are now generating entirely brand new text, images, and videos based purely on the adjusted mathematical weights of the past, who actually decides the baseline of truth? It's an unbelievably complex system running our world, and I enthusiastically invite you to keep analyzing and questioning the models around you. Thanks for joining me for this explainer, and definitely stay curious.